Alright, here we go with the Chapter 2 Homework 1 review. The screen recorder that I'm using just decided to do a massive update, so I hope this is not a total disaster as I try to record this and figure out the new screen recorder. Alright, so this week, as you probably figured out, the homework was a bit harder. It's expected, and as the course really ramps up. And Chapter 2 is a particularly difficult one in the atoms first approach, where we really dive into some of the most difficult concepts that we'll see all semester. So in spite of that, the scores were not bad. I think our average on this homework assignment was about 9.62 out of 12. So that's lower than last week, but that's of course expected with the difficulty of the homework, and overall not a bad outcome. So we will go through then some of the more difficult questions that you had. A few of these were requests from a student, so I definitely appreciate that. They're going to be sort of interdispersed with other questions that I found through Blackboard that you guys had trouble with. I want to arrange everything by topic because there's a few distinct topics that we covered in this section that I want to make sure we go over. So we'll go about maybe about 10 questions or so on a few different topics. So the first major topic was sort of the properties of electromagnetic radiation, energy, wavelength, frequency, and those good things. And there's a couple of equations that we need to remember for that. I think we had some difficulty on a lot of these problems, in part because we're dealing with a lot of numbers in scientific notation, either very large or very small numbers. And so make sure you get accustomed to how that syntax works in your calculator. And of course, in this section, as it will be a theme throughout the course, units are very important, especially here where we have a lot of those prefix units like nano and things coming up very often. Alright, so the first one that I want to go over was, I believe, a question from a student, a request from a student. And we have infrared radiation with a wavelength of 6,200 nanometers. And we want to calculate the energy of one photon of that radiation. So anytime we see energy of a photon, the equation that we have for that is E is equal to H times nu, where nu is the frequency. However, here we're not given frequency, we're given lambda. And we also have to remember then that nu times lambda is equal to the speed of light c, which means that nu is equal to c divided by lambda. So we can make that substitution here and have two equivalent forms of this equation. So depending on whether the problem gives us frequency or wavelength, it's often more convenient to use one of these two forms of the equation. So we'll use the second form, which is that E equals hc over lambda. H and c are just constants, so we don't have to do anything with those, but we have to make sure that lambda is in the correct units. When we write out those constants, 6.626 times 10 to the minus 34 for H, and that's joules seconds. And then C is 3 times 10 to the 8th meters per second. Alright, and this is the key here because this is meters, so we need our wavelength to be in meters. So lambda right now is in nanometers. So if we want to convert that to meters, we have to use the correct conversion, which is going to be 6,200 nanometers, and then we want going into meters with nanometers canceling out. A couple of different ways of writing this. The way I prefer is to use always positive exponents and write 1 meter as 10 to the 9th nanometers. And so when we multiply that out, or more accurately divide it in this case, we should get 6.2 times 10 to the minus 6 meters. And I guess if we're being careful with significant figures, we would do that. So we put that in, and now meters cancel out as we want them to, seconds cancel out, we're left with joules. And so this number in joules, let me calculate it out real quick, get the exact number. So I got 3.21, or 206, I want to be careful with sig figs here as always, 3.206 times 10 to the minus 20th joules. Now, if we go up to our answer choices, I guess here we're treating this number as having two significant figures, but could also be treated as 4, depending on whether you consider those zeros. Anyway, not to get bogged down in those details, because this is multiple choice and sig figs don't matter, especially in this situation, let's look at the answer choices. So it's not these two. We have 3.2, which is the pre-exponential, but this is minus 29, this is minus 26, this one is minus 20. So the wrong exponents for those. Again, these C and D would have been answers you likely would have gotten if you had not correctly converted your answer, your wavelength into meters. And what that leaves us with then is just choice E, between 10 to the minus 20 and 10 to the minus 19. So we see that our number is bigger than 1 times 10 to the minus 20th. It's smaller than 1 times 10 to the minus 19, so that number would fall in that range given by choice E. Alright, so that was the first one. We had a lot of problems like this where it's just converting wavelength or frequency into photon energy. This one is then another type of the same problem, another numerical one. On these problems, be careful with format. So here we're giving you microwave radiation has a wavelength of 1.88 millimeters. I think, again, I suspect a big problem here was maybe unit conversions that we'll go through in a second. We want to know what is the frequency of this in seconds to the minus 1. Remember that seconds to the minus 1 and hertz are the same thing, so don't let that unit throw you off. It's the same thing that we would always calculate for frequency. And we want to enter our answer in exponential format. So here we have to be careful with the formatting. We gave you the format, so following directions is always important in all aspects of life, including general chemistry questions on Blackboard. So make sure you use a capital E when you do this. Make sure you don't put any spaces. Make sure you don't try to put any multiplication signs or anything like that. Just follow the exact format that we specified here. So some of you got this wrong because of formatting, so it's good to do that on the homework and get those mistakes out of the way before the exam. Alright, but let's just go into the problem then. So here we have wavelength and we want to find frequency. So remember that we have that relationship, really the first one we covered for electromagnetic radiation, which is that the product of frequency and wavelength equals C, and we're solving here for the frequency nu, which is going to be C over lambda. As always, our unit for C is meters per second. That's straight from the periodic table. You don't have to memorize that number. And when we divide by wavelength, here we have wavelength in millimeters. So we again have to convert into meters. Remember that milli means 10 to the minus 3, so if we have 1.88 millimeters, and we want to convert that to meters, it's going to be 1 meter is 10 to the third millimeters, or alternatively, again, 10 to the minus 3 meters for 1 millimeter. There's two ways of writing that factor. And so when we divide that out, we get 1.88 times 10 to the minus 3 meters, milli meaning minus 3, so that is fairly obvious. And so we put that here in the denominator for lambda, in the correct units now. And when we divide the two, we get 1.60 times 10 to the 11th seconds to the minus 1. And then when we want to write that in Blackboard, so this is how we would write it in a free response sense, but here we enter it in exponential format with no units, so the correct way to write this in Blackboard would be 1.60 capital E number 11, no spaces. Okay? So that's how we would write the answer in Blackboard, but the more important part is the process to get to that answer. Alright, so that's again just the relationship between wavelength and frequency. So there were a couple questions on that we had trouble with. I think a lot of it was just getting used to, again, scientific notation, unit conversions, all that stuff. A big part of this homework assignment is the Bohr model for the atom, which again stipulates that electrons move in circular orbits around the nucleus. Each of those orbits represents a different energy level and a different distance from the nucleus. That's not a very physically accurate model, but it does do a pretty good job of predicting energy levels and electromagnetic transitions for the hydrogen atom, which is the only thing that has one electron. So really that's the only time when the Bohr model has any sort of relevance. But we're going to do several problems on this one, and the first one just asks us which of the following energy levels is not possible in the Bohr hydrogen atom. So what we have to remember for this is that the equation for the energy levels in the Bohr model is we have the Bohr constant minus 2.18 times 10 to the minus 18 joules. Now, as we talked about in class, more often we're going to use this as a delta E equation, a difference between two energy levels, but here we're just looking at the absolute energy, and so that's just going to be multiplied by 1 over n squared. Now, remember that n here is what we call a quantum number, and it has to be an integer. Alright, so in this question here, if any of these energy levels is going to work out and be a correct energy level for the Bohr model, the value of n that it corresponds to would have to be an integer. So I don't think there's really a shortcut way of doing this other than for each of these 5 answer choices, A, B, C, D, and E, we have to solve for n. So this is going to be our given energy level. We have the Bohr constant, we solve for n. So for choice A, the energy level is minus 2.179 times 10 to the minus 18 joules. And technically the Bohr constant is exactly minus 2.179, although we typically write it as 2.18. If we're being a little bit more precise here. And this one works out to be pretty easily algebraically because those just divide out to be 1. So 1 over n squared is 1. In this case, n is exactly equal to 1. So this would be the ground state energy level for the Bohr atom. So choice A is a correct energy level. In choice B, we get we set the energy level minus 5.445 times 10 to the minus 19 joules. We set that equal to, again, the same equation, 2.179 times 10 to the minus 18 joules, and then 1 over n squared. This time when we solve for n, I'm going to skip the algebra, but you would divide, cross multiply and divide, and then take the square root. We'll do that one for this one real quick. So when we divide both sides, we get, let me see what we get for that. I think I put an extra number in there. That should be 179. So we get basically 0.25 is equal to 1 over n squared. We take the reciprocal of both sides, and we get n squared equals 4. And so that means n equals 2. Alright, so again, the process is divide both sides. And so in this case, when we divide both sides by the Bohr constant, minus 2.179 times 10 to the minus 18, we get 0.25 over here, 1 over n squared. We solve for n by taking the square root and the reciprocal. Alright, so n equals 2 for choice B. We're going to do the same thing for all of them, and I'm not going to go through all the math here because I don't want this video to be hours and hours, but let me do it real quick in my calculator. Oh, sorry. Hang on a second. Alright, well, I paused this to make sure I could give myself time to do this, and there's actually a problem with this question. So occasionally we have problems on homework problems, and I discovered it by doing it here. So what we get for C is n equals 3, so that one works out. D, though, we get n equals 3.16, or in other words, n squared equals 10. Now for E, as I have it written here, I got n equals 1.26, which is not integer either. So let me pause this for a second and double check that real quick. Alright, so I'm back from a little break. Turns out I had a typo in this problem when I put this document together. So choice E is actually not 10 to the minus 18, but 10 to the minus 19. And if you do use that correct number, what you get for choice E is that n equals 4, another integer value. Alright, so there's no issue with the problem in Blackboard, there's just an issue with my typography. And so what we get, sorry, my pen's acting up now. What we get for this one is for choice A, we get n equals 1. Choice B, we get n equals 2. Choice C, we get n equals 3. Choice E, we get n equals 4. But choice D, we get a non-integer n equals 3.16. So choice D would then be the correct answer in this one. So A, B, C, and E all give us integer values of n as long as we use the right exponent for choice E, which I messed up earlier. And so what we're looking for in this one, again, is one that does not give an integer value of n. Alright, so that was a little bit of a train wreck, but will hopefully forgive me for that and move on to the next one. The other type of question that was common for the Bohr model problems was looking at wavelengths or frequencies of radiation that are absorbed or emitted. So here we have for hydrogen, what is the wavelength of the photon emitted when an electron drops from a 4d orbital to a 3p orbital in a hydrogen atom? And here we'd again enter a numerical answer. Alright, so there's always going to be two steps to this whenever we're trying to find wavelength or frequency involved in a hydrogen atom transition. So the first is the Bohr equation, this time in terms of delta E, where we're looking at a difference between two energy levels. It's that same Bohr constant. I'll write it a little bit more precisely, minus 179, but we could write it as minus 2.18, and that's fine. Alright, sorry for another pause. I had a student show up early for office hours, so we're back at it now. And so we're going to use the Bohr equation, which is this Bohr constant, and then it's going to be now a difference in two energy levels, so it's going to be 1 over the final value of n squared minus 1 over the initial value, where again these are the two energy levels that we are traversing between. Now the trick here was we gave you a little bit more information than you needed, which was that we're saying we're going from a 4d orbital to a 3p. Now as this question tells us, or sorry, as this equation tells us, and which is something that we should definitely know for a hydrogen atom, if you have a hydrogen atom, or anything with one electron really, but hydrogen being the only neutral atom that would have one electron, the energy of the electron only depends on n. Alright, so the equation tells us that. It's right in here, just the values of n, and we have to keep that in mind here because we're giving you here in this case 4d to 3p, but all that matters is the value of n. So our initial state is a 4d orbital, which means n equals 4, and then L, which is the second quantum number, is equal to 2. We don't care about L for the hydrogen atom. So for the hydrogen atom, for the one electron systems only, the value of L does not determine energy. And similarly, we're going to our final state, which is a 3p orbital, n equals 3, L equals 1, but again, the L part does not have any determination on energy. So for this problem, all we needed were the two values of n, 4, and 3, and so we plug those in to the Bohr equation. So it's final value of n squared is 3, initial value is 4. We should get a negative delta E in this case because we're going from a higher energy to a lower energy state. And so what I got was minus 1.06 times 10 to the minus 19 joules. That's our delta E. Now that's also going to then be equal to the energy of the photons. Remember that the difference in energy levels that the electron moves between is going to be equal to the energy of the photon that is either absorbed or emitted. So the energy of the photon is equal to this number, and that's also then going to be equal to, as we said earlier, hc over lambda. So here we're looking for the wavelength of that photon. So we get E is equal to hc over lambda. Lambda is equal to hc over the energy of the photon. Now, we have a negative delta E, but the energy of the photon will always be a positive number. We're emitting a photon that's always going to have, there's no such thing as a negative photon energy. And so when we put in the constants here, we get, again, h and c, same two constants that we used before. H times C, and then the energy of the photon again is this number here in absolute value, 1.06 times 10 to the minus 19 joules. And so what I get for wavelength in this case, give me a second, is 1.875 times 10 to the minus 6 meters. But then what we want again is nanometers. What is a wavelength? Nanometers is specified as a unit, so we're going to multiply that by 10 to the 9th nanometers for every 1 meter. And so the final answer we get, where we want, I believe, one decimal place here, is 1875.3 is the number I got. We give you always a little bit of a leeway in terms of the answer, so if you didn't get exactly this number, you probably just rounded something differently than I did. But the point of the matter is we get 1875.3 nanometers. We don't write the units in Blackboard, but those would be the units for that number. That would be considered an infrared photon. Alright, so that was one other, and then last Bohr equation problem, I believe. Yes. Okay, last Bohr equation problem is very similar. Here we want to know the frequency of a photon that will cause excitation from n equals 2 to n equals 6. So this time we're going from low value of n to high value of n, so we're talking about an absorption, so we're looking for the frequency of the photon that will be absorbed. And then once we have that value, determine its log and enter your answer with 3 decimal places. So again, a little bit of extra steps here that are required in Blackboard. The reason we had you enter the log here is because in older versions of Blackboard we couldn't do exponents, so we would always have students take logs to get rid of the exponent. But in newer questions you will have to sometimes enter your answer in scientific notation. So this is a holdover from years past, but we should still be familiar with how to do it nonetheless. Okay, so again we're going to start with the Bohr equation because we're looking for, again, the difference in energy between these two levels. And we're going 1 over n final squared. So here the final value is 6. Initial value of n is 2. So it's the same equation as the last problem, just different values of n. And so this time the delta E that we get I got 4.84 times 10 to the minus 19 joules. Let me double check that number. Yes. Okay, so that's the number. That's the delta E, the amount of the energy of the electron is changing as it goes from n equals 2 to n equals 6. This will also be the energy of the photon. So the photon that's absorbed would have to have this exact same energy value to cause that transition. And again, photon energy is equal to h times frequency. Here we're looking for frequency, so that's the equation we use, and it's actually a little bit simpler than the last one. We're just going to solve by taking the energy of the photon divided by h. Energy here is 4.84 times 10 to the minus 19 joules. H is the same Planck's constant that we've been using over and over. Sorry, 6.626. Get your 2's and 6's mixed up. So joules cancel out, and that gives us an answer in inverse seconds, which is also equivalent to hertz. And so what I got was sorry, this pen is acting up today. 7.30 times 10 to the 14th hertz. So that would be the correct numerical answer. But what we're looking for here again is the log of that. So if we take the log on the calculator, so again be familiar with your log key because we'll have to use that sometimes, we get 14.864. We're going to do this to 3 decimal places. So this is the number we would enter in Blackboard. This again is the numerical answer. That would be telling us what the frequency of that photon is. The log of that is given here. Alright, so it's very similar to the last one, just using a different photon equation once we have the energy of the photon from the Bohr equation. Alright, next we're going to move into quantum numbers here. And so remember that for quantum numbers we have 3 of them that determine an orbital, and then the 4th one, which is the spin. So we'll write those out real quickly. We have n, l, m sub l, and m sub s. And it's helpful to know a little bit about what each of these mean. We also have numerical values that relate them, as we'll see on one of the next problems. But at what this question is dealing with is which of the sort of physical properties or which of the parameters of the orbital or the electron are determined by the principal quantum number n. So for all these quantum numbers, they tell us something about the orbital that the electron is in, or the electron itself in some cases. N is the principal quantum number, and this tells us this is related to, anyway, the size and energy of the orbital. So the larger value of n corresponds to orbitals that are on average farther away from the nucleus. Again, we don't know exactly how far away we are in the quantum mechanical model, but larger value of n means the most probable radius is farther away, and also that the energy is higher. So it does help. And then L is going to determine the shape of the orbital, and also it's going to contribute to the determination of the energy of the orbital if you have more than one electron. So for multi-electron atoms, everything but hydrogen, L also is one of the determinants for energy. M sub L is going to tell us the orientation of the orbital, so it has nothing to do with energy, just orientation. And then M sub S is the electron spin, which is either spin up or down, plus 1/2, minus 1/2. So that's kind of what those 4 quantum numbers mean. We have a table in the notes that summarize that in a little bit more detail. So if we want to know which is not determined by the principal quantum number n, let's look at the answer choices. Energy of the electron is clearly determined by n. And here we're talking about hydrogen. So in fact, for hydrogen, L doesn't even matter for energy, but here we're asking about n anyway. The minimum wavelength of light needed to remove the electron from the atom. Now this is not directly given by n, but remember that the Bohr equation for hydrogen, which only works for hydrogen, which we've been using now over and over again. So if you know the value of n that you're starting with, and you want to go to the situation where you've removed the electron, nf equals infinity, if we know the initial value of n, we can calculate delta E and then calculate the wavelength. So this one is also determined. Let me put check marks next to it because I don't want to confuse you here. So energy electrons determined by n. The minimum wavelength would be indirectly determined by n using the Bohr equation and then solving for wavelength. The size is determined by n. That tells us in the Bohr model specifically how far away the electron is, or really in any quantum mechanical model, it's related to the most probable radius or the most probable distance from the nucleus. The shape of the corresponding atomic orbitals. Remember that shape is determined by L, not by n. So that one is not going to be determined by n, and so that's going to be our answer choice. So A, B, and C are all related to the value of n, the energy being a function of n for the hydrogen atom, the minimum wavelength coming from the Bohr equation indirectly, where nf is infinity if we're talking about removing an electron, and then C is the size of the corresponding orbitals, which again from the Bohr model is directly given as a radius of orbit, but even for other multi-electron atoms, n would be related to size. But the last one, D, the shape of the atomic orbitals will be determined by L, not by n, so that's going to be our answer choice here. Alright, the next one deals with the numerical relationships between the quantum numbers. We have how many electrons can be described by the quantum numbers n, L, n equals 3, L equals 3, m sub L equals minus 1. Now there are relationships again between quantum numbers. So n is going to be integers. And it's what's called our shell number. The number of electrons, if we're just given the n value, is going to be 2n squared. L is going to be 0, 1, 2, all the way to n minus 1. So again, the value of L that's allowed depends on the value of n. If we know the value of L, we're talking about a subshell, the number of electrons would be 2 times 2L plus 1. And then finally, m sub L is equal to negative L all the way to positive L, including 0. Kind of looks like an E. I'll draw it a little bit better as an L. And here, if you know the value of NL and m sub L together, the number of electrons that would be just defining an orbital will just be 2. So the tempting answer to put here is 2 because we gave you NL and m sub L. That means you can only have 2 electrons in that orbital. However, whenever we're doing a question like this, as we talked about in class, the first thing to check is, are these a valid set of quantum numbers? So if n equals 3, which we're given, remember n equals 3 is a valid value for n, 1, 2, 3, and so on. If n equals 3, L can be which values? It can be 0, 1, and 2, up to n minus 1. Here we're saying, though, L equals 3, that's not a valid set of quantum numbers, and so right away we know that there cannot be any electrons that have those 3 quantum numbers. It doesn't even matter what m sub L is at this point, because this is an invalid value of L, given that n equals 3, and so then your correct answer is 0. We don't have to use any of these relationships for the number of electrons that are found in a given shell, subshell, or orbital. None of those matter. So this again would be the number of electrons in a shell. This would be the number of electrons in a subshell. 2 would be the maximum number of electrons in an orbital. But none of these relationships matter because this set of 3 quantum numbers cannot even exist together. So the correct answer would be 0 here. Alright, the last topic on this one, which we'll give a couple of questions about, was electron configuration. And so a couple of the questions we had trouble with just asked us to go backwards here. And so we gave you an electron configuration. I'll write it a little bit bigger here. Helium, 2s2, 2p3. And we want to identify the atom. Now there's actually a little bit of a shortcut to doing this. So we're going to go to the periodic table, and if if we're given a valid electron configuration, all we need to do is figure out how many electrons there are total, because that's going to tell us what the element is. So we go to the periodic table. It's helium 2s2 2p3, so helium has 2 electrons. So the total number of electrons, we have 2 from helium, we have 2 from the 2s2, 3 from the 2p3. This is going to be a 7 electron atom. And then if we go back to the periodic table, the element that has 7 electrons would be nitrogen. So that's really all we'd have to do here. So nitrogen is the is the name of the element. However, we also have to identify the number of unpaired electrons. Now, that was a short way of finding out what the element is. Just assume this is a valid electron configuration, which it is, add out the total number of electrons, and then use the atomic number from the periodic table to get it. If we wanted to look at the configuration in more detail, it's going to be helium 2s2, that's going to be 2s1, 2s2, 2p3, 2p1, 2, 3, also takes us to nitrogen. So this whole column here, where nitrogen is part of, the last subshell that was filled would be the p subshell, and it would have 3 electrons. So this would be 2p3, 3p3, 4p3, 5p3, 6p3. So anything that ends in p3 in the ground state anyway would be one of these elements here. Nitrogen is in the second row, so that makes it the 2p section of the periodic table. Another way to identify that that's the correct one. But we also have to look at number of unpaired electrons. And again, for unpaired electrons, we go to the partially filled subshell, which is 2p. 2p has 3 orbitals. Each one can hold a maximum of 2 electrons. And when we're putting electrons in for the ground state, we have to follow Hund's rule. So we have 3 electrons. We're going to go 1, 2, 3. Remember, before we pair up any electrons, we individually fill each orbital, all with the same spin. So all 3 of these 2p electrons are going to be unpaired. So we have 3 unpaired electrons in the ground state of nitrogen. And so the correct answer then would be n, 3, with the space in between as we specified. Again, following directions is important to make sure that Blackboard interprets your answer correctly. Alright, so once we know the configuration, we can count number of electrons or look more detail at the subshells to figure out the element, working a little bit backwards on the periodic table from what we did in class. And then once we have that configuration, we can write out the partially filled subshells to figure out how many electrons are unpaired. Now the next question here is, of the following elements, which has occupied d orbitals in its ground state neutral atoms? Alright, so here we're looking for occupied d orbitals, so we do have to consider the full electron configuration, or at least the partial ones. So let's just go ahead and write out all of these electron configurations. A good way to practice that. So we have Ba, which is barium. So Ba is where is that? Here on the periodic table, number 56. And so for the configuration of barium, we go again to the noble gas that comes before it, which is going to be xenon. And then after xenon, we go to this row of the periodic table. This is 1, 2, 3, 4, 5, 6. So this is 6s1, 6s2. So if we just write out this shorthand configuration, xenon 6s2 for barium, it's not obvious whether or not there are d orbitals. So we do have to think a little bit about those core electrons from xenon. Now if we look at xenon here, xenon is in the 5th row of the periodic table. So before xenon, we have the 4d block, which is these 10 here. We also have the 3d block. So xenon is going to include filled d orbitals. And so this one would have occupied d orbitals in its ground state because, again, xenon, we don't want to write the full thing out, but this core xenon configuration, as we abbreviated it, includes filled 3d10 and 4d10 subshells. Okay? Because as we go to xenon in the periodic table over here, number 54, we have to traverse both through the 3d and then later on through the 4d before getting all the way to xenon. So we have filled 3d and 4d orbitals. So choice A would have occupied d orbitals. We could choose that. Let's verify that the other ones do not have d orbitals. So if we go to calcium, calcium is going to be a little bit above that on the periodic table, number 20, same column. So calcium is going to be, argon is a noble gas that comes before it, and it's going to be 4s1, 4s2. We see that calcium occurs before the 3D block, so there are no D electrons in calcium. Filling up to here, we just went through the 1s, 2s, 2p, 3s, 3p, and 4s subshells. So the way we would write this configuration is argon 4s2, but in this case the core electrons do not include any D electrons because it only requires us to go through s and p blocks. Silicon is up here now for number 14. The noble gas before it is neon, Ne. So it's going to be neon, and then silicon is going to be 3s2, 3p1, 2. So it's going to be 3s2, 3p2. And again, neither the core nor the valence electrons involve d orbitals. And then finally, if we go to, sorry, what was the next one? My bad. Phosphorus and chlorine, those are right next to each other. Phosphorus is going to be neon, and then it's going to be 3p3. Chlorine is going to be 3p5. So those are in the same row of the periodic table. They just have a few more electrons. So all three of these are similar. Now that's a good way to look at it by just looking at the full configuration, and hopefully it gave us a little bit of practice doing that. However, what we can notice is that if you remember the different blocks of the periodic table, the first D block, the first section of the periodic table that involves D electrons, starts here at number 21 with scandium, Sc. So remember that these 10 columns here in this middle section we call the D block, and those are the elements that have D electrons. So until you get to atomic number 21, you're not going to have any D orbitals filled, and then all of the elements after 21 will at least have partially filled or completely filled D orbitals. So this is looking for which has occupied D orbitals. So any of these that are atomic number less than 21 are going to have no D electrons, because atomic number 21 is the first time when we start putting D electrons in. So this is going to be atomic number 56, I believe it was. This is 20, let's see, and silicon is, 14, 15, 17. Alright, so that's another way to look at it, is looking at the atomic number 14, 15, and 17. So anything below 21 does not involve D electrons, so B, C, D, and E, which are 20, 14, 15, 16 for their atomic number, you would not be putting any of those electrons in the D orbital, so only choice A would be one that involves partially or completely filled D orbitals. Alright, so there's a lot of different ways of approaching this problem. Again, the periodic table is going to be what you need to look at to figure out which of these would have D orbitals filled in the ground state. Alright, finally, the very last one. We didn't exactly cover this yet, but I think we can help at least understand it, and this was requested by a student, so I want to make sure I go over it. So we have this electron configuration, krypton 5s2, 4d10 5p2. We want to know for the fluoride of E what's the most likely formula. So it's helpful to also think about the electron configuration of fluorine, which is going to be, if we go to the periodic table, fluorine is going to be 1s2, 2s2, 2p1, 2, 3, 4, 5. Alright, so this is going to be 1s2, 2s2, 2p5 for fluorine. Now when you're thinking about what's the formula of a certain compound, we're going to get into this in more detail in Chapter 3, but for now what we would want to appreciate is that when elements form bonds, they want to completely fill all of their available subshells. So if we look at the partially filled subshell, this element here, I didn't identify it, but if we go to the periodic table and figure out which one that is, 5p2 is going to be, let's see, 2, 3, 4, 5, that's tin, Sn. So the element here is Sn, although that's not too important for this problem. When we look at partially filled subshells, so we have 5p2, 2p5. So starting with fluorine, fluorine has a 2p5 partially filled subshell, Remember that the p subshells can hold a maximum of 6 electrons. Again, if you forgot that, look at the periodic table. This is the 2p, or any of the p subshells have 1, 2, 3, 4, 5, 6 positions. So that means they can have a maximum of 6 electrons. And so when we do this, we get, this is 2p5, so this needs one more electron to fill its 2p, which means it's going to form one bond. Because when elements form bonds, they're sharing electrons, they're getting electrons from other elements. And so if this needs one more electron, it'll form one bond to do this. If we go to tin, this has a 5p2 subshell. This needs 4 more electrons, which means it would want to form 4 bonds to be able to do that. So if each fluorine forms one bond, and tin wants to form a total of 4 bonds, that means tin needs to partner with 4 fluorines, SnF4. In this case, we're giving it generically as E, although the real element is tin, as we saw from the configuration. It's going to be EF4. So choice E would be the correct one, because this element needs to form 4 bonds to completely fill up its p subshell. Each fluorine is able to form one bond because it only can take one more electron into its 2p, and so that combination tells us that the fluoride would be EF4. So this was a little bit of a step above what we needed to do in Chapter 2, but it got you thinking critically about these electron configurations and what they mean. All right, that takes you to the end of this this homework review. If you have any additional questions, please come see me, and I'd be happy to help you with them.